This is Physics 1060, Descriptive Astronomy, Lecture 15. In today's lecture we're going to talk through chapters 14 and 17. Cosmology. Cosmology is the study of the structure and evolution of the universe as a whole. How big is the universe? What shape is it? How old is it? How did it form? What will happen in the future? Well, the first thing we need to look at is Hubble's law. Every object is moving away from us. So does Hubble's law imply we are at the center of the universe? No, it doesn't. We can understand this by looking at the expansion of a loaf of raisin bread. So here we have a loaf before it rises. And let's just look at all the raisins inside. So these raisins are all situated, and they're not moving through this bread. They're stuck in the bread. Now, as the bread itself rises and gets bigger, because it's rising, every raisin moves away from every other raisin. Not because they're actually moving through the bread, but the bread itself is expanding. Now, as that happens, two objects that are close to each other, the distance between them, this and this, is pretty small. So the distance change between here and here is small over a certain amount of time. Now, the further you are, the bigger the distance change. So I've had a larger distance change between these two than these two. But I've done this distance change, this expansion, at the same amount of time. So therefore, this raisin appears to be moving away from the home raisin at a slower rate than this raisin. So this is what Hubble's law is telling us. The further away something is, the faster it seems to be moving away from us. Doesn't mean that there have things actually moving through the galaxy or through the universe. But what it means is the universe itself is expanding like the raisin bread. So Hubble's law implies that the whole universe is expanding, not that we are at the center of it. And today astronomers think of space itself expanding, not galaxies moving through space. So the raisins in the above example are not moving in the bread, but move with the bread as it expands. The galaxies are not moving through space. Space itself is expanding. So, in the early years of the 20th century, astronomers envisioned the universe as a static place with only the Milky Way and a few companion galaxies. It was not until the 1920s that astronomers realized the universe was filled with other galaxies millions of light years apart, and that the universe itself was expanding. Now, no matter which way you look, you see about the same number of galaxies. The galaxies are not spread smoothly, but clump into groups. The smooth clumping implies a similar distribution for the whole universe. Now contrast this with the sky's Milky Way, implying that we are a disc-shaped galaxy. Because everywhere we look we see about the same, it implies that the whole universe has a similar distribution to what we see all around us. Now in general, a galaxy obeys Hubble's law. The speed of recession is proportional to its distance, the proportionality given by the Hubble constant. Again, the motion is due to the expansion of space itself, not like a bomb fragments going through the air, but like buttons attached to an expanding balloon. If I glued buttons all over a balloon and started blowing it up, as I blew it up, every two buttons would appear to be moving away from each other on the surface of the balloon. Neither one of them is moving on the balloon, it's just the balloon itself is getting bigger. That's the way you need to think of galaxies in the universe. So are we at the center? The recession of distant galaxies often leads to this misconception that we are at the universe's center. However, because space is expanding, no matter where you are located, galaxies move away from you. There is no preferred center. The lack of a preferred central location is called the cosmological principle. So if the universe is expanding, and we know the rate at which it's expanding, that means at some point things were closer together. So let's kind of play the history of the universe in reverse. So we run the universe's expansion backward. It implies all mass becomes confined to a very small volume that we call the permeable atom. Now, if we assume galaxies have always moved with velocities they now have, the Hubble's law gives an age of the universe of about 14 billion years. Now, in 1823, Heinrich Ober's offered Olber's paradox. If the universe extends forever and has existed forever, the night sky should be bright, but of course it isn't. Olbers reasoned that no matter which direction you looked in the sky, a star's light should be seen. If I have an infinitely old universe, and it goes on and on forever, then eventually, no matter where you look, there should be a star, and the light from that star should be coming towards us. So the sky should be completely bright with stars. We don't see that. Therefore, we know the universe can extend forever and has not existed forever. Finite age and speed of light means only a finite volume of starlight is available. In other words, the night sky is dark. So what do we know now? The universe is expanding and is filled with very low energy background radiation. The radiation expansion imply the universe began some 13 to 15 billion years ago, depending on the expansion rate. The universe began as a hot, dense, violent burst of matter and energy called the Big Bang. Now, many people consider how the universe started as only a religious question. For scientists, though, the approach is to go out and make observations, what can tell us something about what happened. What we'd really like to be able to do is to be able to look back in time. But we can do this because light takes time to travel from place to place. So light from distant galaxies has been traveling for billions of years. What we see is galaxies as they were billions of years ago. In this way, we can actually look into the past. We can get an idea of how cosmologists can use the idea of looking back in time by considering the controversy that raged in the 1960s between two rival cosmology theories. The rival to the Big Bang was the steady state, which stated that there was no beginning to the universe. As the galaxies move apart, new matter is formed to take its place, so the average density of the universe never changes. The steady state theory had an advantage in that it was more simple. Now, we can test these theories by seeing how far apart on average galaxies were in the past. And as we look back, and this was the present, the steady state should be the galaxies were about the same distance apart in the past. The Big Bangs should say the galaxies were closer together in the past. And when we actually look at the galaxies further away, we see that galaxies are closer to each other in the past. Therefore, the Big Bang theory is the one that fits our model and our observations. Today, there are better tests than this between the two theories, but this is the simplest to explain. Now, when we apply the laws of physics, we actually predict the right amount of helium that we see at present day. Most helium in our universe dates from the Big Bang, not from the stars. However, all other elements were formed in the stars or in stellar explosions. Now, when atoms were first formed, photons were produced. Radiation from this period can still be detected. It's called the primordial background radiation. And we can detect this with special telescopes. The Kobe telescope is one. And we detect it as a faint microwave hiss. And by studying the fluctuations in the background, we learn something about what the universe was like before there were any galaxies. Small fluctuations in the density of the gas in the young universe grow to form galaxies and clusters of galaxies. Understanding exactly how this works is a vibrant area of current cosmology. Now, what caused the Big Bang? That is not a science question, and scientists should not try to answer the what caused it. That is a philosophical question, not a scientific one, because I can never test it. I can never go back and find out what caused it. That makes it in the realm of philosophy. So what about this cosmic microwave background? The proposed very dense early universe implied that it must have been very hot, perhaps up to 10 trillion degrees Kelvin. Now, it was proposed that the universe expanded, and as it expanded, it cooled. That's the ideal gas law. As things expand, as the volume goes up, the temperature goes down. You can figure this out anytime you open a bottle of pop. When you open up a Coke, for example, it immediately gets cold. As the gas that was pressurized in there is released, it cools down in temperature. So, it was proposed that as it expanded and cooled, the radiation that existed at that early time would survive to the present as microwave radiation. This radiation was actually accidentally discovered by Arno Penzias and Robert Wilson in 1965, and has since been referred to as the cosmic microwave background. So very hot gas is going to give off a very high energy light. Say it's blue light. It's actually probably hotter than that at 10 trillion degrees. But now I've got this light coming from between galaxies, and it takes a long time for it to travel. Well, during the time that it's traveling, space itself actually expands. And as space expands, the space everywhere expands at the same rate. And so that blue light expands into a red light. Now, if we actually look at the cosmic microwave background, it follows a perfect blackbody spectrum with a temperature of about 2.7 Kelvin, or just above absolute zero. So current theory suggests that the early universe consisted of protons, neutrons, and electrons. The initial hot, dense state allowed nuclear reactions to create helium. Now, based on the estimates of the early universe's expansion rate, about 24% of the matter should be transformed into helium. And that's in great agreement with what was observed in old stars in the Milky Way and in other galaxies. Now, that's not the only measurement. We can do different measurements on deuterium, which is hydrogen with an extra neutron, and lithium, and all these support the hot, dense early universe theory. The early universe's high temperature and density imply that it had a very simple structure. Mass and radiation mingled in a manner unlike their sharp distinction today. The radiation was so energetic that it easily transforms to mass, and mass and radiation, or mass and light, behaved as a single entity. Now, E equals mc squared tells us that not only can mass be transformed into energy, like is going on in stars, but that energy, say in light, can be transformed into mass. The creation of mass, however, must come in pairs, ordinary matter and antimatter. So, for example, the antiparticle of the electron is the positron. The antiparticle of the proton is the antiproton. This is because we need to conserve charge. Light has no charge. As it comes in, it has enough energy that it can create a particle and an antiparticle. The charge of these two things must be opposite and equal. Now, the same thing can happen in reverse. If I have a positron and electron that come and hit, they can give off light and convert mass into energy, or energy into mass. Now, based on Hubble's law, the Big Bang occurred about 13 to 15 billion years ago. Again, you should think of this as an explosion of matter and space, not matter into space. This is not an explosion like a firecracker that blows up and sends pieces off in all these different directions. It's that the space itself is exploding and dragging everything with it, and things are coming apart because space is pulling it apart. Now, to understand what happened, we take the laws of physics as we know them and apply them to a very hot, dense matter that must have existed when everything was pressed together. If we apply the laws of physics, we can deduce a history of the universe. And we can go back to very, very early times. And it's a logarithmic scale. So we're looking, maybe at 10 to the minus 33, 10 to the minus 35 seconds. That's a really short amount of time. That's about where we're at. We don't understand what happens all the way to 0, but we're getting close. So at 1 microsecond after the Big Bang, the temperature is about 10 to the 13 K. That's hot enough for photons to create quarks and antiquarks. Now, a quark is a subatomic particle. A proton, for example, if you break it apart, will break into 3 different quarks. 1 up quark and 2 down quarks. So we can start creating the quarks, the things that the subatomic particles are made out of. And at this time, at 1 microsecond, the diameter of the universe is smaller than the Earth's orbit around the Sun. The universe at this point is expanding at nearly the speed of light, and as it's doing that, it's cooling rapidly. The lower temperature no longer produces quarks and antiquarks. Now, those who study subatomic physics show that that dictates that existing quarks and antiquarks annihilate, but they annihilate asymmetrically, and that leaves an excess of quarks. The surviving quarks then combine to form protons and neutrons. At 5 seconds or so after the Big Bang, the universe actually cools enough that all matter that could be created is created. There's not enough energy left as it cools down for matter to continue to be created. Now, at 3 minutes after the Big Bang, the temperature is a few 100 million degrees. And at this point, about a quarter of all the protons fuse into helium, in that same proton-proton chain we talk about that's going on in stars. For the next 500,000 years, we get further cooling and expansion. Electrons begin to bind to protons to make hydrogen molecules. And this is referred to as the recombination era. At the end of this period, photons and matter go their separate ways. Photons can't move through a plasma when protons and electrons are all separate from each other. But as soon as they combine and we get neutral atoms forming, then light and matter can go their separate ways. Now, if we consider the ages of several galaxies, we know that galaxy formation had to start very soon after the recombination era. So protogalaxies formed from the gravitational collapse of gas clouds, these gas clouds of the hydrogen and helium that formed earlier. Gravity is too small a force to create galaxies in the time scales that are needed. So there is a need for dark matter to speed things up. Dark matter forms clumps around which protogalaxies form. Areas rich in dark matter clumps form large-scale galaxy chains and sheets. Areas deplete of dark matter form voids. How this all works is still considered an unsolved problem that people are trying to figure out. So as we look at the timeline for the universe, the temperature started off very hot and cools down to about the 3K that we are today. We had at 10 to the minus 33 seconds, we have an inflationary period, and we talk through all these. This is a logarithmic scale, and here we are now, about 10 to the 10th years. Now eventually, the fuel's going to run out. We get dark stars and dark galaxies, if expansion happens forever. But whether it's going to happen forever is still a question to be solved. Now, what was the state of the universe before 1 microsecond? Well, it was even hotter and denser than what we talked about. Actually, the universe is smaller than the size of a proton. And at that scale, gravity is no longer a force of attraction, but one of repulsion. The repulsive force creates this violent explosion, which cosmologists call inflation. That inflationary period happened in a very short time scale. We can't really even imagine how short of a time scale it is. It began at 10 to the minus 35 seconds and lasted until 10 to the minus 32 seconds. Inflationary period ends where the previous Big Bang theories begin. The inflationary models of the universe mark the frontier of our understanding of the cosmos and give tentative answers to several unsolved mysteries. Some models suggest creation from nothing. Others suggest existence of other separate universes. Still others posit that the universe has 10 or 11 dimensions that we only perceive 3 and time would be 4. This is string theory you may have heard of. Finally, these models also try to explain why space is so flat and how all the forces of nature relate to one another. Before the start of the inflationary period, 3 of the 4 fundamental forces, the electromagnetic, the strong and weak nuclear forces, are joined together in a matter described by grand unified theories, GUTS. As the universe inflated, symmetry breaking separated their forces that releases energy. And this energy was then used by the false vacuum, a non-zero energy state with negative pressure. And according to general relativity, a negative pressure manifests itself as a repulsive gravitational force, lasting only for the brief inflation period. So, at this point I want you to stop and I want you to watch the Nightline Big Bang Theory video. This explains a little bit about, it was about 20 years ago or so, the discovery of the fluctuations in the cosmic microwave background, which really is one of the crowning achievements of the Big Bang Theory. So now, where's the edge of the universe? Everyone worries about where the edge of the universe is, or at least scientists do. It is historically one of the great paradoxes. In the traditional view of the universe, there's no simple answer. But there are a couple of ways of realizing that there are more subtle ways of looking at the question. The first is something called the light horizon. Since the universe is only about 13 to 15 billion years old, we really can't see anything further away than 13 or 15 billion light years. So the age of the universe limits the distance we can see since the speed of light is finite. In other words, if we're here, there is a visible horizon. There might be more stuff out here that we don't know of. We can never see it because the light from this has not had enough time to reach us yet. The maximum distance one can see is called the cosmic horizon. The space within the horizon is called the visible universe or the observable universe. There may very well be more to the universe beyond what we can see. The distance to the cosmic horizon gives a rough measure of the radius of the visible universe. For a 14 billion year old universe, the radius is 14 billion light years. So, we know the universe is currently expanding, but what about its future? Will it expand forever, or will it stop and collapse? Expanding forever means that as the stars consume their hydrogen, the universe will become black and empty. It's called an open universe. A universe that collapses as a big crunch, which is the opposite of the Big Bang, might lead to another primeval atom, leading to perhaps the birth of another universe. This scenario is called a closed universe. Or the expansion speed of the universe can become zero when the universe has reached infinite size, and that's called a flat universe. The energy content of the universe depends on what type of universe we are in. An open universe has a positive total energy. A flat universe has a zero total energy, and a closed universe has a negative total energy. In principle, if we measure the energy content of the universe, we can tell what type it is. The energy content of the universe is the sum of the positive kinetic energy and the negative energy of gravitational binding. So basically, how much mass it has in it. The mass density of the universe gives an equivalent means of determining its total energy content, and that's actually a lot easier to measure. To determine if the universe is open and closed, we compare the density of the universe to the critical density. The critical density is 3 times Hubble's constant squared over 8 pi g. So, if the density is greater than the Hubble, than the critical density, the universe is closed. If the density is less than it, the universe is open. The critical density is 10 to the minus 29 grams per cubic centimeter, or about 1 hydrogen atom per cubic meter. And this is about 25 times more than the mass density determined from the observed stars and gas. So based on the amount of observed mass, the universe looks open. But what about dark matter? Well, the estimated amount of dark matter is just enough to close the universe. So, is that a coincidence, or is there something deeper happening here? Another way to ascertain the universe's fate is to look at very distant galaxies in the past, to see how fast the universe's expansion has slowed. And interestingly, using supernova in very far and faint galaxies as distance indicators, it appears that the universe is actually speeding up, not slowing down. How is this possible? Well, Einstein's general relativity equations actually include a cosmological constant that represents a repulsive force. Einstein actually considered this his biggest blunder and wanted to throw it out, but he didn't. And now, as we start to look at it, we say maybe that was true. So when the expansion of the universe was discovered, the cosmological constant was thought to be 0, but the latest measurements imply that this may not be the case. A universe that is speeding up implies it's actually older than previously thought, helping further solve some star-age discrepancies. So Einstein's general theory of relativity is built around curved space. Now, curved space is not easy to visualize, but there are two-dimensional models that can help. Positive curvature, also called closed, resembles the surface of a sphere. Parallel lines meet, and triangles have interior angles with a sum greater than 180 degrees. Negative curvature, also called open, resembles the surface of a saddle. Parallel lines never meet, and triangles have interior angles with a sum less than 180 degrees. Flat curvature, what people typically think of space, parallel lines do not meet. Triangles have interior angles exactly equal to 180 degrees. So in principle, one could directly measure the interior angles of a triangle or an equivalent geometric arrangement, but to date, practical limitations prevent being able to do so. Now there's another way of measuring the curvature of space, and the cosmic microwave background provides this way. It is extremely uniform across the sky except for tiny variations in brightness from place to place. The spatial sizes of these variations can be predicted based on conditions in the early universe. Analysis of variations indicate that the universe is flat with a non-zero cosmological constant. We can only imagine a world of 3 dimensions. So we can get some idea how limited this view is by imagining a world of only 2 dimensions, such as on the surface of a piece of paper. This gives the idea of Flatland. Flatland is a romance of many dimensions. It's a short novel that Edwin Abbott published in London in about 1884. And Abbott described his interactions with beings who live on a flat plane of 2 spatial dimensions and showed how we might perceive the existence of higher dimensions. Now again, expansion of the balloon is an example of the expansion of the universe. Where's the edge of a balloon? Well, certainly if we imagine a balloon in 3 dimensions, we can say, well, I can reach down, I can touch the surface of the balloon. But what if I was an ant on the surface of the balloon? Where's the edge? Well, there's no edge. I can walk around in any direction and I never hit an end. That's a closed surface. Nowadays, cosmologists can calculate the properties of a universe with different number of dimensions, even though we can't visualize them. So the crucial question about the future of the universe is whether or not it will continue to expand forever. And again, it depends on an average density of 10 to the minus 29 grams per cubic centimeter. the average density is higher than this, the universe collapses on itself in the future. If it's smaller than this, it expands forever. It's actually another example of escape velocity. Remember, the escape velocity is larger the higher the density of the object. The visible matter is not enough to stop the expansion, but if there's a lot of dark matter, then the universe may be critical. There are some attractive theoretical reasons for believing the universe has a critical density. This would again support the idea that there are large amounts of dark matter in the universe. It's another reason why cosmologists favor the existence of dark matter. So how do we determine the density of the universe? One of the most powerful ways of measuring the amount of dark matter in the universe is gravitational lensing. Right, remember, light from a distant galaxy is bent by passing near the enormous mass that's in a galactic cluster. As a result, one can see more than one image of a distant galaxy. By studying the locations and shapes of these images, we can work out how much dark matter is in a cluster. We can even map out where it's at. And remember, we can use quasars as a method of determining gravitational lensing. So a quasar goes by a galaxy, it's bent around it, and the light appears to come from one place. So we look, here's the central galaxy, and here are 4 images of a quasar behind that galaxy. Today, we now believe that over 90% of the universe is dark matter. In other words, we know just about nothing about 90% of the universe. So I've mentioned dark matter several times. It's time to stop dancing around it and talk about what is dark matter. Now, ordinary matter is atoms, and the more fundamental particles that make up atoms, like protons. Ordinary matter is visible in the sense it can absorb light, it can scatter light, and emit light. Dark matter seems to be different. It appears to respond to gravity, but nothing else. So, let's examine the possibilities of what dark matter is. Now, the first is hydrogen and helium. If dark matter were hydrogen and helium gas, we would see absorption lines, because hydrogen and helium cannot be solid in space. Therefore, it cannot be hydrogen and helium gas out there. Well, what if it was the matter out there was rocks or terrestrial type planets, things that don't shine light by themselves? The problem there is that these type of things are made out of heavy elements. By heavy elements, we mean things heavier than hydrogen and helium. If dark matter were rocks, then the ratio of heavy elements to hydrogen would have to be more than 10 instead of only about 1%. All of our theories of the origin of the elements, which are theories that are solidly backed up by observational data, would have to be discarded. So it can't be rocks or terrestrial type planets. What about black holes? Well, the only way we know of making black holes is when big stars die. If there had been thousands of times more big stars in the past than we now estimate, we would see plenty of evidence of this in the galaxy, such as a higher abundance of heavy elements. What about neutrinos? Remember, these are the tiny particles that are produced by radioactivity or infusion in the stars and travel almost at the speed of light. There are vast numbers of neutrinos in the universe left over from the Big Bang. Recently, there has been evidence that neutrinos may have a tiny amount of mass, but it does not seem to be enough to account for all the dark matter. So the next is a MACHO. That's an acronym for a massive compact halo object. The idea here is that there are zillions of small stars or large planets. They either do not have nuclear reactions, like Jupiter, or have so few that the stars hardly shine at all. They're so faint that they hide from our telescopes. They're called halo because there's evidence that dark matter in our galaxy is spread out in the galactic halo, where the globular clusters are, rather than the disk of the galaxy. The problem is that there needs to be an awful lot of them, more than you get by extrapolating the number of normal stars. One way of looking for them is to watch for them to move in front of a distant star and amplify the light by gravitational lensing. This has been tried. And the answer seems to be that there are not enough machos to explain dark matter. So the last idea is something called a WIMP. That's an acronym for a weakly interacting massive particle. The idea is that there is a new kind of particle, separate from protons, electrons, or quarks. So to verify this idea, scientists want to find actual traces of these particles. In other words, they want to be able to create them in a lab. This is an enormous challenge to physicists. This is the type of work that's being done in CERN and the other supercolliders. They're trying to have enough energy to create new particles and see if they can find something that would match this WIMP. Well, does dark matter matter? Although there's a lot of dark matter in the universe, it's very spread out, not concentrated at the Earth or even in our solar system, so there's a negligible amount of it around here. You don't have to worry about walking into dark matter. But the future of the universe depends overwhelmingly on the amount of dark matter in the universe. The current bet is that there is not quite enough dark matter to cause the universe to collapse back on itself. The even greater mystery is dark energy, and that's the current name for this force that seems to be making the universe expand faster instead of slower. That acceleration is discovered when scientists were looking to see if Hubble's law still applied accurately at super large distances. They used a certain type of supernova explosion, which always has the same power output, and used this to measure the distance to very distant galaxies without using Hubble's law. They expected to see that the dark matter in the universe was slowing down the expansion, but in fact they found an acceleration that implies a force pushing the galaxies away from each other at large distances. We have very little idea what causes it. It's very hard to study. This is right on the frontier of science. It might even be wrong. So that's really it. We've now moved out and covered the entire universe. We've seen what we have, and now we're off in the place where we're still exploring, still trying to ask the questions, trying to understand the cosmology, or the cosmos as a whole.